Hello, and firstly welcome to this preliminary presentation for the 11th Annual Information Technology, Electronics and Mobile Communication Virtual Conference, which will be held in Vancouver between the 4th and 7th of November 2020. My name is Daniel Mitchell, and I am a postgraduate research assistant at the Smart Systems Group based at Heriot-Watt University, Edinburgh, Scotland. The following work is a partnership between the Offshore Robotics for Certification of Assets Hub, Microsense Technologies Limited, and the Smart Systems Group. Today I am delighted to be presenting an evaluation of millimeter wave radar sensing for civil infrastructure. A brief overview of this preliminary presentation includes frequency modulated continuous wave FMCW radar for non-destructive evaluation, where the general benefits of FMCW technology is discussed. Next, the technical challenge which engineers face when evaluating the integrity of civil infrastructure is presented. Then I outline the solution to the technical challenge and value created from millimeter wave sensing. The laboratory-based experiments are then presented. Experiment 1 is titled Embedded Material Analysis in Sand, and Experiment 2 investigates embedded material analysis in Darney sandstone. To provide an overview of our unique and patented method of sensing, several benefits for engineers and robotic platforms have been outlined. The sensor can be utilised for non-contact and non-destructive analysis, is highly tunable in terms of range, field of view and depth of view, one data acquisition per second and sub-second if required, requires low power, is of military specification and highly integratable into existing systems such as robotic platforms or installation within infrastructure, is suitable for metallic targets which can provide external state of health, suitable for composites and low dielectrics for internal state of health measurements, has the ability to produce real-time results on a platform-mounted or handheld device, and lastly, operates accurately in poor lighting and opaque conditions such as smoke, steam and mist. Civil infrastructure requires cyclic integration of design, construction, inspection, repair, maintenance, renewal and upgrading to ensure safety and meet societal requirements to access resources. Reinforced concrete has many benefits for construction, however, is prone to early deterioration due to the effects of carbonation, which is a reaction with CO2, and chloride-polluted concrete due to salt. This results in corroded reinforced concrete, which can significantly deteriorate the integrity of a structure. Current investigations of civil infrastructure are unreliable and do not give an accurate representation of the integrity of a structure. This is due to civil engineers relying on visual inspections and acoustic emissions. Many problems often start off internal to the structure and do not display visual cracking until a severe amount of deterioration has formed. So how do we solve this technical issue? The development of our FMCW radar presents a unique method of non-destructive evaluation for fault prognosis of embedded rebars. This method of sensing has been demonstrated in the following laboratory-based experiments which examine the return signal amplitude received at the radar. It is important at this stage to emphasize that this sensing method enables for distinct subsurface material responses and properties which are not visible externally, hence early detection of faults within a porous structure. The value created by millimeter wave radar sensing and this research looks to reduce risk and operational costs via proactive risk mitigation. The first experiment conducted included the embedded material analysis in sand. The aim of this experiment was to investigate the return signal amplitude of buried materials within the sand by utilising non-destructive evaluation for A. the shape of embedded material and B. the depth of embedded material by utilising a copper sheet and a copper rod. Additionally, the type of sandstone material embedded within the sandpit was investigated. The FMCW radar was positioned 10 cm from the surface of the sand. The test material was then buried at incremental depths. The FMCW radar was then initiated, where the results are displayed in real time for the return signal amplitude. The second experiment conducted utilised the embedded material analysis in Darney sandstone. This experiment was conducted to evaluate the use of FMCW radar for detection of rebars within sandstone. The FMCW radar's antenna was positioned 10 cm from the surface of Darney sandstone on the right-hand side of Figure 2. On separate occasions, 3 variables were complete within the aperture. These were a dull drill bit, a stainless steel ruler, and 3 milliliters of water ingress. The results of each variable demonstrated a difference in return signal amplitude and phase. Our detailed results will be released at the conference between the 4th and 7th of November. At this point, I invite you to view my colleague's preliminary presentation, which has also been published at this conference, and also utilises the same FMCW radar sensor for structural health monitoring of wind turbine blades. This paper is called Asset Integrity Monitoring of Wind Turbine Blades with Non-Destructive Radar Sensing and is available on our YouTube channel. Please also find more information at the Smart Systems Group or Orca Hub websites to view our latest research presentations, public outreach, and news features. I would like to thank you for viewing our presentation and look forward to any future engagements.